Hello everyone, welcome back. Okay, so last time we learned about centroids, center of gravity, center of mass, center of volume, center of area, center of pressure, center of pretty much anything. It was all the same equation. It's more or less a weighted average. But while that's really easy to do if you have an equation, well, it's not always easy, but you can do it with an equation. Or if you got some very simple shape. What about when you got very complex shapes? So today we're going to talk about composite bodies, a way that you can take a complex shape, break it up into a bunch of simple shapes, and go from there. Oh, there we go. Okay, so using this, we'll be able to find the centroid or center of mass or anything else you need to using composite bodies. So why do we need this? Well, what about this? I mean, there's no equation for that. And if you look at it, well, okay, I've got a rectangle here, and a rectangle here, but what's the center of gravity of an eye? I mean, at least in this case, it's doubly symmetric, so I would know that it's at the exact center, because the center of gravity is always along an axis of symmetry. This one, though, it's singly symmetric, so I know it's along this axis, but it's it's somewhere in here. I have to figure out. Luckily, with the method of composite bodies, we can just say, okay, well, we're going to more or less take an average, kind of the center of gravity of this and the center of gravity of this to figure out where it actually is. Now, why do you need to know this? Well, because honestly, that's where the weight acts. There's a whole lot of different things that happen at that point. In fact, the centroid is the point where if you were to bend this beam, it would go from tension on the top to compression on the bottom. Like if I were to draw it, find out about this in solid mechanics. It's a fun little detail. No. I'm not done with that page. Silly thing. Pen. There we go. So if I bend a beam, and this is this bottom beam, the T shape, there is a center of gravity that goes all the way through it. It's centroid. And on the top, you can see that that would be stretched because it's getting longer, and the bottom is compressed. And this point right here is where it's neither compressed nor stretched. It happens at the centroid. So that's very, very important to understanding the stress, strain, force distribution inside of your beam. Okay, so method of composite bodies is going to help us to do this. Let's keep going. And then look at this. Whoa, this is terrifying. Look at all these items. There's one right here, and here, and here, and here, and here, and here. Oh, it's just horrible to look at. How are we going to find the center mass of this? Now, luckily, it's not saying we're going to find the center mass of this item. It gives you the center mass, or the centroid, or the center of gravity, whatever you want to call it right now, for each of these individual items. In this case, it would be the center of gravity. Centroid of this shape would be a different point, actually, because it's not homogeneous. And so we get it for each of the items, and we can work with that. Otherwise, this would be a nightmare to try to find the centroid of. I would probably have to use some 3D modeling software to do it accurately. But why do we need this? Well, we need to know where that weight's going to be acting so we can understand the support reactions, okay? What are the support reactions? That's one way to do it. We can sum all these forces and figure out sort of where they're acting. Okay. So what we're looking at right now is a composite body made of 3 different particles. Okay, we got particle 1, particle 2, and continue onward until particle N. We're trying to figure out where the center of gravity is. Now we can tell what the resultant weight is. We just add them all together. Weight 1 plus weight 2 plus weight 3 plus weight 4, all the way through, and I get the sum of the weights. And we can also sum the moments about the y-axis. Okay, so it's the distance from the y-axis to each of those points, more or less, to their centroid. Since it's a little sphere or a little particle, we're just saying right to its center. But if it was a rectangle or something, you'd have to go to the centroid of that shape. And so we add them all up here. And we remember that all of this is going to be equal to the actual centroid of my system of particles times the resultant weight. And then just like before, boom, magic, this equation reappears, this sort of weighted average equation. And just remember this, that now instead of being an integral, I'm a sum because I have individual shapes or points that I'm adding all together. If I had an equation, it would turn into an integral. If I have lots of shapes I can break apart, it's a sum. And sometimes you have sums of integrals. It can be, because you might have two shapes which are both defined by an equation. So there's lots of different ways you might want to do this, but either way, it can all come back down to a sum or an integral. So same equation, weighted average, and this is what we do. This is what we use every single time. Never forget this equation. It is extremely, extremely helpful. And also by replacing W with M, we get the center of mass, which is the same thing. Okay, now let's talk about composite body. Now most industrial objects, they don't have nice simple shaped parts. Well, luckily we make everything in cylinders and rectangles. It doesn't happen. So in that case, you're going to have to look at it and say, okay, can I break this up into simple shapes? Like you can see right here, well, that's a triangle, that's a square, that's a circle, that's a half a circle. And then from that, I can figure it out. Okay, well, I got a triangle, I know where the centroid of that is, and a square, I know where the centroid of that is. A circle, I know where the centroid of that is, and a half circle, I know where the centroid of that is. You can look them up, they're actually in your book. Same thing with this. And so using that, we can then do that sum, that weighted sum, to determine, well, where is their centroid of the overall parts. Okay. As a note, empty space is considered to have a negative value. Okay, it's going to be a negative value. You have to subtract it out. Filled in, positive, empty, negative. Don't forget that when you're doing your sums. So now let's look at a method, just like the steps to follow in order to solve these kinds of problems. So go ahead and pull all of these up, and then we can talk about them. So first, divide those bodies into pieces that are known shapes, and wholes are considered as pieces with negative weight or size. You might be calculating the center of area or the centroid. In that case, it's negative size. Make a table. This table is super helpful. I'll show you in the problems as we do these example problems how it works. But make a table. But the first column for the segment number, the different shapes, 1, 2, 3, 4, how many shapes you did. The second column for the weight, mass, or size, what you're trying to do. The next column for the moment arms, and finally, all the columns you need for the rest of the calculations. You're going to add them all together, and then you're going to calculate the centroid using these equations. Okay? Using those equations. I do notice that my little bars here got moved over. I'm not sure what's caused that. So that's supposed to be X bar, that's supposed to be X squiggly hat. So as normal, this will become a lot more straightforward once we do an example. So for now, just keep this in your mind and go ahead and watch the next video when you're ready. So I'll see you all next time as we try working out some example problems on calculating the centroid and center mass. We got this. See y'all later. Bye-bye.